David Spears, civil engineering instructor at Texas Tech University, talking about solids CE 3303, exam number 2, page 2 of that exam, showing a statically indeterminate axial deformation problem. What we have is a rigid bar supported at pin A up here at the top with two wires attached at this point 6 feet down and 12 feet down further from that, points B and C, and they prevent rotation about the pin at A when the 5 kip force that's 12 feet down from the top from pin A, when that 5 kip force is applied. Each wire is identical. It has an area, cross-sectional area of 0.05 square inches and a Young's modulus of elasticity 31 times 10 to the third KSI. First part was asking for an equilibrium equation, which is a sum of moments equation, taking moments about point A, the pin, to eliminate those forces, which there's an X and a Y up there. Counterclockwise is positive, it's equal to 0. I have the forces in the wire, TB and TC as I've called them in this little free body diagram. Their moment arms are, and the moment direction is clockwise about point A, so they're negative. Negative TB times its 6-foot moment arm minus TC times its 18-foot moment arm plus the applied force 5 kips times its moment arm of 12 feet. Doing the math, moving these terms to the other side of the equal sign, I get 6 TB plus 18 TC is equal to 60 kip feet. That's the moment caused by that 5 kip force. So, simplifying, eliminating some terms, I get it down to TB plus 3 TC is equal to 10 kip feet. Next part was a compatibility equation. Give the compatibility equation. So that's based on deformation. And so because the bar is rigid, it doesn't bend, draw this little triangle. Deformation at B, where the wire is attached, is equal to that amount, and down here where wire C is attached, the deformation of that wire is that amount right here. By similar triangles, that angle is equal on both of them. I have the deformation at B, delta B over 6 is equal to the deformation at C, delta C over 18. So moving these terms up, multiplying by the opposite side, I get 18 delta B is equal to 6 delta C. And simplifying that, I get 3 delta B is equal to delta C. And because I know the deformation of that wire, the elongation, because the wires are under tension, they're going to elongate, is PL over AE, I can just substitute PL over AE in for these deformation values, and I get 3 TB L over AE is equal to TC L over AE. The length, the area, and the Young's modulus are the same for each one, so I can eliminate that term. Simplify this compatibility equation down to 3 TB is equal to TC. Now I've got two equations, two unknowns. I can plug into one and solve for the other. I'm going to plug this equation into this equation. So I'll rewrite it, TB plus 3TC is equal to 10. But I want to plug in the fact that 3TB is equal to TC into here, substitute that for TC. I get TB plus 3 times 3TB is equal to TB plus 9TB is equal to 10 TB, and that's equal to the 10 kip feet from this equilibrium equation. I can divide by 10 both sides by 10, and I get TB is equal to 10 over 10 is equal to 1 kip tension. Therefore, TC is 3 times that, or 3 kips. It's also in tension. That's the force in wire C. That's the answer to the third question on that page. And finally, the elongation of the wire B, it's the fourth part of that page. It's just simple PL over AE. The force in wire B is TB. It's 1 kip times its length. I got to get my units all correct, so 6 feet long, that's the length of that wire, times 12 inches per foot, divided by the cross-sectional area, 0.05, divided by Young's modulus. I get the elongation is 0.0465 inches.